Hello, students. Welcome to the Engineering Geology and Hydrology course. In the last class, we studied the definition of fracture structures, the geometric elements of faults, and the basic types of faults. Today, we will continue with the second part of Chapter 3 on fracture structures. The main focus of today's class is the composite types of faults and how to identify them in the field. Identifying faults in the field is the key point of this class. In our last class, we studied the definition of faults, their geometric elements, and the basic types. Today, we will focus on two main aspects. First, the composite types of faults. Second, the field identification of faults. First, let's look at the composite types of faults. In reality, faults rarely exist in isolation. Within the crust, they often coexist with other structures and combine in certain patterns. Based on their arrangement, we can categorize them into step faults, grabens and horsts, and imbricate structures with similar attitudes that are arranged in parallel. As shown in the top right diagram on the right, each fault steps down in a staircase pattern, much like a set of stairs, which is why we call it a step fault. Grabens and horsts are opposite dips and similar properties, as shown in the dynamic diagram in the middle. If the rock block between two faults, which rise relatively, we call it a graben. We call it a horst. Grabens are reflected in the landscape as long and narrow valleys or elongated basins, while horsts often form blocky mountains, such as the Tian Shan and the Alps, which widely develop horst structures. Thirdly, imbricate structures refer to a series of thrust faults with roughly the same attitude arranged in parallel, with the hanging wall of each fault thrusting upwards in sequence, like shingles overlapping from the top of the valley. For example, the diagram in the lower right corner is an imbricate structure. Secondly, field identification of faults. Most faults in nature are not clearly exposed on the surface due to subsequent erosion, destruction, and coverage. Therefore, the existence and type of faults should be judged based on direct evidence such as stratigraphic structures, and indirect evidence such as geomorphological and hydrological aspects. Firstly, we can determine the presence OFA fault based on the discontinuity of structural lines and geologica, bodies, such as the sudden interruption of geological boundaries, the cutting of dikes, and the offset. Then we can distinguish the faults exist or interruption of early formed folds and faults. Recognition signs include the repetition and absence of strata. In layered rocks, the strata are continuous. If there is asymmetric repetition or a certain layer is missing, it is generally caused by a fault. The inherited repetition caused by faults is different from that caused by folds. The repetition caused by faults is unidirectional, while the repetition caused by folds appears symmetrically, so we need to distinguish between the two. Third, field identification sign is the structural features on the fault plane or within the fault zone, such as the scratches and steps on the fault plane, the traction phenomenon of the fault, as well as the presence of fault gouge or fault rocks. These two photos show the scratches and steps on the fault plane. We can clearly see that due to the sliding and friction between the rock blocks on both sides of the fault plane, obvious friction marks will be left on and near the fault plane, as well as the traction phenomenon. The traction phenomenon refers to the phenomenon where the rock layers near the fault bend in an arc shape due to the frictional force of the fault when the two sides of the fault slide against each other, as shown in the diagram on our right. The rock layers near the fault plane have some curvature, which is the traction phenomenon of the fault. The direction of this curved part can indicate the movement direction of the fault block. These are some fault gouges and fault rocks on our fault plane and field identification sign. Fourth, the geomorphological and hydrological characteristics. The geomorphological and hydrological characteristics of faults mainly include fault scarps, fault triangle faces, abrupt changes in mountain ranges and plains, and sudden offsets. In the water system, we can identify the existence of faults through these signs. This is fault scarp and fault triangle face. The fault scarp refers to the steep cliff suddenly formed by the relative sliding of the two sides of the fault, which we call the fault scarp. As shown in the photo on our left, the fault triangle face refers to the triangular steep cliff formed by the erosion and cutting of the fault scarp by water flow, which we call the fault triangle face. We also have abrupt changes in mountain ranges and plains, such as flying peaks and tectonic windows. In the field, we can also determine the existence of faults based on the offset of the water system, such as in this photo, where the water system is suddenly interrupted at this location, which proves that there is a fault here. In this class, we mainly studied the composite types of faults, which mainly include step faults, Robbins and Horst's, imbricate faults, as well as the field identification of faults. We need to learn to determine the existence of faults based on the discontinuity of geological bodies, the repetition and absence of strata, the characteristics of fault zones, and the geomorphological and hydrological features. We have basically finished studying the content of geological structures. So, what impact do these geological structures have on our engineering construction? We will study the relationship between geological structures and highway engineering construction in the next class. See you next time.